Hi, everybody. It's Professor Mitchell. We are finally finishing up Chapter 3 today, looking at Section 3.6, Measures of Association Between Two Variables. The goal of this section is to examine two descriptive statistics that measure the linear relationship between two variables. And those are called the sample covariance and the sample correlation coefficient. The sample covariance, which is denoted S sub xy, measures the, sorry, I've got some things blocking stuff here, measures the direction of the linear relationship between two variables. A relationship is linear if the scatter plot of the independent and dependent variables has a straight line pattern. So here's the formula for the sample covariance. And I'll show you, of course, how to use it here in just a couple minutes. So you're going to make a table that's going to have a few columns. First thing you have to do is calculate the mean for X and Y, and then make a column where you subtract the mean for X from each X value, and another column where you subtract the mean for Y from each Y value, and then multiply those differences together. And then you add those all up and divide by one less than the sample size. The covariance is useful in describing the direction of the relationship, but not the strength of the relationship. So what they mean by direction is whether the relationship is positive or negative. If the points in the scatter plot go up and to the right, that is a positive relationship. If they go down and to the right, that's a negative relationship. But again, that's really all the covariance tells you, is whether that relationship is positive or negative. Okay, just make sure. All right. And then the sample correlation coefficient measures both the strength and direction of the linear relationship. So you might ask, well, why bother with the sample covariance? Well, two reasons. Number one, you need it to calculate the sample correlation coefficient anyway. And that's pretty much the main reason, actually. All right. So the correlation coefficient is calculated by taking the sample covariance and dividing by the product of the sample standard deviations. And the sample correlation coefficient is called R sub xy, or sometimes just R. All right, so here's an example. A car dealer wants to examine the relationship between the number of sales representatives and the number of cars sold per week. Suppose a sample of 6 weeks is selected, and you see the data here. We're going to record two values for each week. First, the number of sales representatives, and then the number of cars sold. And if you just examine this table, you can see that the trend is definitely when there are more sales representatives, they sell more cars. That makes sense, doesn't it? All right, so we're going to confirm that by calculating the sample covariance. Okay, so first of all, you see the scatter plot here, which seems to confirm, or at least back up, that this relationship is positive. These points are going up and to the right. Okay, and then the calculation looks like this. So this is the type of thing that I've been doing in Excel lately, because I'm not always happy with the way they show it, but I thought this was just fine. This is exactly the way I would do it. So first we calculate the mean for X, and that comes out to 3.5. Now what they did, they made a whole column just for X bar, which I don't normally do, but it might help make it a little bit more clear. So notice in this column, X sub I minus X bar, they get that by doing 2 minus 3.5 is negative 1.5. 5 minus 3.5 is 1.5. 3 minus 3.5 is negative 0.5. Etc. And then they do the same thing for Y. So the mean for Y comes out to 7. So here are all the 7s listed here. 4 minus 7 is -3. 10 minus 7 is 3. 7 minus 7 is 0, etc. This is the same thing that you do when you're calculating the sample standard deviation using that first formula that we talked about. And remember that you can check to make sure that you haven't made a mistake up to this point by adding these values together and just confirming that they add up to 0. Okay? So it's pretty easy to see that these and also these are going to add up to 0. And then the way that we get this last column is by taking this number times this number, right? So -1.5 times -3 is positive 4.5. 1.5 times 3 is 4.5. -0.5 times 0 is 0, and so on. All right, so now we're going to add all these values together. They add up to 10. So that means that the sample covariance is 2, or they wrote it as 2.0 because I think I've mentioned this before. Normally, these statistics are rounded to one more decimal place than you have in the original data. So that did come out to a positive number. A positive value implies a positive linear relationship. A negative value indicates a negative linear relationship. And a covariance close to 0 indicates no relationship between the two variables. Now, one disadvantage of the covariance, as I mentioned, is that it only tells you whether the relationship is positive or negative. So it's kind of hard to say with the covariance, you know, what do they mean by close to 0? How close to 0? Well, that kind of depends on the size of the original data. So I would say if you're looking to say that there is no relationship between the two variables, it would probably be safer to do that from the correlation coefficient, which we will talk about next. Okay, so don't freak out. Using the same example with the 6 weeks of car sales, remember that the first thing that you have to do is calculate the covariance, which we've already done, and then you divide by the product of the standard deviations. So I'm not going to go into detail on that calculation. You see them do it here their way. I would normally do it using a table. Actually, I would just use the same table that we use to get the covariance. So at this point, you might want to pause the video and just verify that you get the standard deviation for X is 1.05. The sample standard deviation for Y is 2.0. So when we take 2.0 and divide by the product of 1.05 and 2, we get 0.952. Now I want to caution you, when you put this in the calculator, make sure, so you don't have to put parentheses around these two numbers, and in fact, I wouldn't recommend doing it that way when you put it in the calculator. What I would recommend is put parentheses around the whole entire product. Here, let me see if I can write on this so you'll understand what I'm talking about. You definitely have to have parentheses around this whole entire product, because otherwise your calculator will think that you want to divide by 1.05 and then multiply the answer by 2. All right. Another thing that I want you to try really hard to remember, and this is actually coming up on the next slide, so let's look at that. The correlation coefficient comes out to 0.952. So what does that mean? The sample correlation coefficient, R sub xy, indicates both the strength and direction of the linear relationship between the independent and dependent variables. The values of R range from -1 to 1, And I would actually go further than what they say here. They say that a -1 is a strong negative relationship. Actually, if your correlation coefficient came out to -1, that indicates a perfect negative relationship, which means all of the points perfectly line up in a straight line, and that straight line has a negative slope. And similarly, a correlation coefficient of 1 would be a perfect positive relationship. The points would line up on a straight line, and the slope of that line would be positive. When r equals 0, there is no relationship between x and y. And here I would say as long as r is close to 0. It's rare for r to come out to exactly 0. So if, again, this actually depends on the size of the sample. How close to r would you have to get before you would say there's no relationship? Let's just say rule of thumb, I would be skeptical about any R value that's less than 0.5 or bigger than -0.5. In other words, between -0.5 and 0.5, okay? But if it's close to +1 or close to -1, that means it is a strong relationship, either positive or negative. So our correlation coefficient came out to 0.952. That is a very strong positive relationship because it's so close to 1. All right, here's a nice picture that shows you some different situations for the correlation coefficients. So these first two pictures back up what I was saying a minute ago. If the points line up perfectly along a straight line, that means perfect positive correlation. The correlation coefficient would be 1. Here it would be -1. These points all line up, and the slope is negative. An R value of 0.6 would indicate a moderately positive relationship. This one here is a relatively weak negative relationship. So you can see as we move to the right here, the points look less and less like a straight line, right? And here they're all over the place. So that R value would be close to 0. All right, if you would like to use Excel to check your answers, and please only to check them, all right? If you're taking my class, I will probably look at your work for this just to see that you know how to do it manually, but it's perfectly okay to use Excel to check your work. So the formula for covariance is covariance.s, and here you would put two ranges. First, the range of x values and then the range of y values. The same thing for correlation coefficient, that's CORREL. And again, range for x, range for y. Notice that the letter S in covariance stands for sample. We didn't talk about population covariance, but that is a thing, all right? So if you happen to have the whole population, you can use the command covariance.p. P for population. And that's going to take care of it not only for section 3.6, but also for chapter 3. So we will see you next time when we start chapter 4.